Happy Friday, everybody. To recap what we have covered so far, operation system gives us thread concept in order to be able to concurrently run different operations, even if we have only one CPU core by using context switching. But creating threads is very expensive. This is why .NET provides us a thread pool abstraction, which has a pre-created amount of threads for us, which we can reuse. We covered the differences between CPU-bound and IO-bound operations. We also highlighted that it is very important to never block any thread, because if we do not block any thread, we can afford to run many concurrent input-output operations, thousands or hundreds of thousands of them at the same time, without the danger of starving the thread pool. We saw ways to use thread pool using a key user work item or tasks. We saw how we can chain tasks, as well as how we can chain them using async await instead of continue with method, which is much more convenient. Also, we discussed that there is no thread, basically, when there is any input-output operation is happening. It's just an event that switches task from the in-progress state into the completed state. And we checked synchronization context and why we need to call configure await on every await in our library code, especially library code. So the summary from everything that we covered so far, I guess we can say that the key to building scalable applications is to never block any threads. So today we are going to cover synchronization between threads. So yeah, we can run different work on different threads. However, most of the time we need to somehow orchestrate these threads. So one thread needs to update some data that is needed to be accessed from another thread. Or maybe both threads need to update data at the same time, but in some specific order, etc. How we can do that, we'll cover today. In order to synchronize multiple threads, .NET provides us synchronization primitives. Let's look at this example. We have 1000 tasks. I'm calling this method 1000 times, which will return us a task that will wait for 500 milliseconds and attach a continuation to itself, which will then add a new GUID to this list of generated GUIDs. So I'm scheduling 1000 of these tasks to be run at the same time, and I'm waiting for them just to complete before I write to console that it is done. If you run this example, we'll see that in our generated GUIDs, only 967 GUIDs were added. And if I run it again, we'll see that there are 977 of them now. So what is happening here? Thing is that list is not thread safe structure. A thread safe meaning that it can be used from different threads at the same time. Since it's not thread safe, we cannot use it from even two threads at the same time, not even to write with one thread and to read with another. It might not insert items, how we saw here. It might even throw exceptions. It might behave incorrectly, or it might even get into the corrupted state. So it's very bad to use non-thread safe objects from multiple threads at the same time, because then we cannot expect any stable result. How we can fix that example? .NET provides for us one of the synchronization primitives is called semaphore slim. Semaphore slim is just a primitive that allows only one thread to enter with this configuration. This configuration means that only one thread can enter this lock. This is how it's being used. So if we call this method from many threads, the first thread that will call wait async method on the lock, it will be able to enter the rest of the method. As soon as it enters the rest of the method, any other threads that are coming here, they will wait on this line until this lock is released. So only after first thread has called this release method, only then second thread or third thread or some random thread, the next one that is lucky, will be able to go inside that method. And all the rest will again wait, because they will wait until somebody releases this lock again. So if you run this example again, as you can see, there are 1,000 operations, and there is a lock here now. And inside we're waiting for half a second. So we'll wait for half a second multiplied by 1,000. It's really a very long time. So for the sake of this example, I'll just wait here for 1 millisecond. Now we'll wait for 1 second, right? 1,000 tasks, each waiting for 1 second. So let's wait. Okay, we waited for about 2 seconds, as you have noticed. This is because this construction, waiting for a lock, is expensive on by itself. So whenever you are using locks, you need to consider whether you need them or not, because every time you are using synchronization primitives and are locking on something, it incurs a performance hit. So your code will run slower when you are locking on something. This is why we only want to lock wherever is absolutely necessary, and to try to avoid locking as much as possible. And obviously, because we are locking here in this example, and we are just executing this method 1,000 times, it is completely inefficient because we are basically just executing 1,000 times this method in a row, just additionally incurring the overhead for locking. So this whole thing can be just rewritten with for loop and without any concurrency at all. It will be faster. So now if we check our generated GUIDs, you'll see that all 1,000 of them will be entered here because we are entering these GUIDs one by one using our lock. However, this code is a bit incorrect. Let's imagine this situation. What if some part of this code before a release happens will throw an exception? Well, in this case, we reach kind of a deadlock, not even a deadlock, but since this method will never complete, it will never write done, because as soon as the first thread enters here, it takes the lock, then it executes the code, but then exception happens, and nobody releases it. So 999 of other threads will just be stuck on waiting here forever, because nobody will ever release this lock. In fact, if we pause the application and we look at parallel stacks window, we go to tasks view, we'll see that we have right now 999 async logical stacks, which means we have 999 tasks unfinished doing something. However, if we check our threads on parallel stacks window or in the threads window, we can see that the only thread that is currently running our code is the main one, the first one. This is because this semaphore slim synchronization primitive, it doesn't block the thread. The thing doesn't block the thread. It's completely asynchronous. So our wait async operation, it just returns a task with this continuation, same as any other await operation, which is very cool. So we are not using any threads. We created 999 tasks, but they are all just logical tasks. No threads are being used in the meantime. So even if we forgot to write try catch here and we didn't release it, our memory and performance doesn't suffer. This is in fact the only synchronization primitive that allows us to asynchronously not block the thread. All the other primitives are blocking. So whenever you have async code, consider using semaphore slim. Also, semaphore slim has another method, wait, which you can use to block the current thread. But obviously, it will block the thread and will not, it will use all the threads. And then thread pool will try to create as much threads as it can. For half a second, it will create each thread with half a second debounce until thread pool has 1000 threads in this example, because we are never releasing the lock. All right. So now let's go through other synchronization primitives that we might use in non-async code when we have no other choice but to block current thread. The first one is the most and the most simple one is basic monitor or lock keyword in C# language. So if there is some object, if you have some reference to some object, it can be completely new object like I created here, or it can be even the parent object, or it can be any other object like list, like some variable. But it's a good practice to create a new separate object, an empty object that doesn't have any data in it, etc., for locking purposes. So we created a new object, and here in our method that we run for 4 times, we are entering with our monitor. Then we are using try finally in order to, if here some exception happens, we will still exit from the monitor. So exit is like release from semaphore slim. This is a way to fix that issue that we had with our synchronization example. By the way, yeah, I didn't show it. So here, if exception happens, we are doomed because we didn't call release. This is a proper way to implement it. We await our semaphore slim, and then we always include any code into try finally, and only in finally we release. Always include that block when you are using semaphore slim or any other synchronization primitive, because even if you think your code cannot throw an exception, it can always throw an exception, even assigning to variables or adding an item to a list. Imagine if your machine on which your code runs has 500 megabytes of memory and the application already used 490 of it. So the next operation, whatever it is, it might throw out of memory exception, for example. And if you do not have that block of code, you will never release it. So always include any code in try finally after you wait for lock. So getting back to that example with our simple object lock, we can enter a monitor with method monitor enter, and we can exit a monitor with method monitor exit. However, the C# language provides a syntactical sugar for us in order to not write the try finally and to avoid manual bugs if you forget to write it. It's a magic keyword lock where you just specify your lock object and you have these constructions. It's very similar to using block for disposables. It will automatically for you wrap all your code into try finally, and then finally it will exit the monitor. So these two methods are completely identical. Obviously, this will block current thread if many methods will run this method at the same time, because it's not async. The only async primitive is semaphore slim. So yeah, another primitive synchronization primitive that we have is semaphore. So yeah, semaphore slim is kind of like a slim brother of a big semaphore, because semaphore is a system-wide concept. It's not a .NET concept. Where semaphore slim is just a .NET concept that is very slim and executes operations without big performance issues. Semaphore creates a separate operation system-wide object. It's the same as using new thread, basically. New thread is creating new operation thread completely out of the scope of thread pool. A semaphore creates a new semaphore system-wide object, which takes resources to create, takes memory, takes CPU cycles. Unfortunately, there is no semaphore pool in .NET like thread pool. So whenever you need a real semaphore, you need to create it using this code. Now, what is a semaphore? Semaphore is also a synchronization context like a semaphore slim that has similar methods, wait1 and release. But it is system-wide, meaning that it can be named like this with some unique name. It's a very naive example. Unique will be some generated GUID of your application plus some of your text that you want to uniquely generate. And this semaphore will work across different processes. So imagine you created one application where you have this code, and then you created completely different application, even maybe in different programming language, where you just create a similar instance of a class that creates system-wide semaphore, and you specify the same name. Then between these completely two different applications running in completely two different processes on the same machine, you'll have that synchronization. So only one process will be able to enter this method, and second process will need to wait if it needs to enter it until the first one has released semaphore. Both semaphore and semaphore slim can be configured. It's these first two numbers, like I showed you in this example. This is 1, 1. Here I have 2, 2. So what they mean, the first number is initial count and second is maximum count. This is the amount of concurrent executions this semaphore can allow. So for example, if we have maximum count as 2, then actually two methods, two threads can enter the semaphore at the same time. But the third one will wait until at least one of these methods will release semaphore. And the initial count is how many threads can initially enter the semaphore. So if we put 0 here, then no threads will be able to enter here at all until from some other place of code somebody calls release, which will increase that initial count to 1. And then the thread will be able to enter, and this initial count will be back to 0. There is another object in .NET which is called mutex. Mutex is just a shorthand for semaphore with parameters 1 and 1. So yeah, it's just a faster way to create a semaphore that only allows one thread. It also has a boolean instead of number, initially owned, which is if it's true, then first somebody needs to release it, because then on the moment of creation, it will be already taken. There are a couple more event-based synchronization primitives in .NET. For example, wait handle, event handle, manual reset event, auto reset event, and countdown event. These three are extending these two. So these two are just base classes. They're being used for some low-level manipulations. We'll maybe cover them if we have some time on advanced meetup. Manual reset event is being used like this. So, for example, we create manual reset event, and then on some background thread, after 2 seconds, we set it, which means that it is now set. And later, when we wait for wait one method, it's waiting until it's being set. Similar to task completion source a bit. So as soon as it is set, this line will unblock the thread and allow execution further. And since it's a manual reset event, we need to reset it manually. So we need to call a reset method on it later. If we do not call it, then the next line, wait one, it will also allow proceeding, and all these lines will execute as soon as we call set method here. Auto reset event is the same, just it auto resets. So as soon as we call set, we'll be able to go to this line, but as soon as we call wait one, it will reset. So on this line, we'll wait again until somebody calls set on it. And countdown event is similar to manual reset event and auto reset event. It just has a countdown. So you specify some number, for example, 5, and it will not allow you to go further until set will be called 5 times. So each time set is called, the countdown is basically counting down. One more synchronization primitive is reader-writer lock slim. Imagine we have this situation. We need to allow users to read data concurrently. So even if there is 1,000 threads reading this data, let them read it, or like not read it, but execute our method. Let readers read, like execute a method 1,000 times concurrently, however they want, etc. But as soon as we need to write something, we need to, first of all, wait until all readers have finished reading operation. Second of all, not allow any new readers to enter that read method. And only after all readers have completed reading and all new readers are still waiting and not entering, only then we are entering write log and updating the value. It's similar to how memory barrier works, I guess. So this is an example. We are sleeping for just 5 milliseconds, and we are entering read log, and we are writing to console that we are entering read log and waiting for another 10 milliseconds, and then we are exiting read log. So we'll write this very, very fast, very, very often. However, once per 2 seconds, we are going to enter write log. And after we entered write log, we'll write to console that we entered write log, and we'll wait for 1 second. And only then we'll exit write log. The result of this application looks like this. So we are writing a lot of read. And then, as you can see on the last line, sometimes once per a second, we are writing writer log, and we are waiting for 1 second. This is because no other reader operations are allowed to go inside the reader log until that write operation is complete. In fact, if I pause application when we encounter write line in the console, you'll see that, like if I mark, you'll see that there are a lot of threads being used by our code. And they are all like 23 threads currently are executing our methods. This is because I wrote here thread sleep and not task delay. So essentially every thread that enters this log, it blocks the thread. That's why we have so many threads and all of them are being used. Now there are a couple of low-level synchronization primitives as well. Not really synchronization primitives, but I'd say helper classes. There is a spin lock and spin wait. What is this? Spin lock is a synchronization primitive that is very, very lightweight. Only thing it does, it just waits for in a loop, like for example, for loop. It just iterates in a for loop many, many times, millions times per second, hundreds of millions times per second until somebody releases that lock, and then it allows you to proceed. So this spin lock, it actually uses your CPU quite a bit, but it uses less resources and is more performant than any other synchronization primitive. So if you have a very, very fast operation, and by fast I mean not milliseconds, but even nanoseconds, then you might want to use the spin lock instead of create a new synchronization primitive for your like instead of locking on a synchronization primitive for your very, very fast operation, because if you have a nanosecond operation and you wait on some lock, then probably you'll spend even more time during performing the operation of wait on that lock than even your operation. So in this very performant case, a spin lock can be used. Spin lock is used like this. You have method enter and you have method exit. Spin wait is just a means to wait one cycle. So this spin lock, it doesn't just iterate in an empty loop. Instead of that, inside of that empty loop, it uses spin wait to wait. And this spin wait has a method spin once. So this method executes basically in a couple nanoseconds or something like this. It's very, very fast method. It executes in a very short time. And spin lock is just doing while true spin once, something like this. So if you're creating your own primitives based on spinning, then you can use this spin wait in order to not re-implement any kind of logic like this and just use it in a loop until you're waiting for something. One more thing that we have in .NET, it's very handy sometimes, is interlocked. Interlocked is not a complete synchronization primitive in that it doesn't create like a scope that will only one thread will be able to enter. Instead, interlocked is a primitive in order to atomically update value. For example, let's see this example. While I less than 1000, we just incremented. It's not important. It's just we are running this code 1000 times. We create 1000 tasks. Inside every task, we just wait for 1 second and we increment this value to +1. So if it was 10, we expect it to be 1010, right? So let's run it and we'll see this value printed in console, 995. This happens because some threads update value concurrently at the same time. So if value was 50 and both threads at the same time try to update this value, they will both increment it to 51. This plus operation is actually not thread safe. It will create artifacts like this. What we can do instead, we can use an atomic operation of incrementing a value by a reference. Interlocked add method does just this. We are passing the value through a reference to this variable, and we are saying by how much we want it to be incremented. So now, without any locking at all, well, there is some kind of locking happening inside of add method, but it's very, very minimal. We can see that Now our value is 1010. Interlocked has many other cool methods to atomically change values. Also exchange, it will change this value into this value. And if other threads are trying to access it, they will access it only after it's changed because it's an atomic operation. Compare exchange, it changes the value only if this value is equal to this. And there is also increment, which it just increments it, so it not adds values. Here we can add 5, but we could rewrite this example to just increment, because increment just increments it by 1, and etc. There are a couple more methods on interlocked, but yeah, if you need some very, very lightweight synchronization, you might be able to use interlocked. There are a couple more things in .NET. These are pretty much all most important synchronization primitives, maybe even all of them, except these ones. These ones are somewhat advanced things. In .NET, there are things like volatile thread memory barrier, also method thread abort, not synchronization primitives. I just have it here to not forget about it, and thread interrupt as well. We will talk about this if we have time on advanced meetup, but in general, every primitive that we covered today, you will probably need only them in any project. This one's a very advanced topic, which you will probably need only if you're writing some kind of device drivers that needs to be asynchronous, or if you're writing a code that you need to optimize and every nanosecond counts. Now imagine a production scenario. You have a cache, right? You have a cache, and you want, if many threads call your method, you wanted to only get the value once, and for the other threads return already the value that you got and cached. So this is a simple implementation of this kind of cache. We have some cached value here, and inside our method we are checking if cached value is not null. So if it's set, we are returning it. That's all fine and good. Then we are, in case it's not set yet, we are entering a log using semaphore slim. So only one thread will be able to enter here. However, inside we are duplicating this check. This is a pattern that you should be able to recognize from many projects, and if you're writing this kind of cache yourself, you will probably use it in 99% of the cases. It's a good pattern to recognize. Why we need to duplicate this logic inside our log? It's simple. If we do not duplicate it and just get the value and set it to this variable, all the other 100 or somewhat threads are already waiting on this log. For example, if your method is called 100 times at the same time. So all the other 100, as soon as you release this log, all the other 100 threads will come inside. And if you do not have this check to return already cached value, then they all will run this code again. So you'll have 100 calls to your API if here, for example, you're calling an API. So for all these threads that are already waiting for a log, when you are performing this operation by one of your threads, you need to have the logic duplicated here in order for them to then return already cached value as soon as they enter the log. All right. One more thing I wanted to tell you. This simple log that we have here, like object log, and I showed you an example that we create a new object and we just use the log construction here. In .NET 9, which will come out in November, it's already in release candidate, but it's not released yet. They have added a new object type, which is basically called log. So it was added exactly for this purpose. Instead of creating new objects, we'll create a new object of type log. And use absolutely the same code. So we'll just have this log object. The advantages of it being that it's internally being optimized, so our code will start working slightly bit faster in this case. Now, it's all and good. We are able to insert our GUIDs here, right, using our log construction. However, logs are slow. And if we just need to enter some value into a list and not perform some more complex logic, then it makes sense to use specific collections for that instead of using custom logs. .NET provides system collections, concurrent collection, something like this, a namespace, which contains a bunch of collections which are essentially thread safe. So now we'll cover these thread safe collections. Thread safe collections allow you to call any methods on them thread safely. So you can basically call any methods on the collection from any of the threads that are running concurrently without any locking or without thinking about data inconsistencies, because these thread safe collections have already internal logs implemented in a more performant way than you can implement using custom logging. That will be optimized for your use case, and you can just use that class. So let's see an example of thread safe collection. First, let's look at the queue. So in .NET, we have queue class, right, that allows us to queue some items into it. We can enqueue item and we can dequeue item. Enqueue adds an item, dequeue returns as the item and removes it from the collection. Alternatively, there is a concurrent queue type that allows us to execute this operation concurrently. So in this example, I run 100 tasks, each of which is enqueuing a book. And at the same time, in parallel, I am trying to dequeue a book. So this concurrent queue, it has a method tryDequeue, which returns Boolean. If it's false, it means that there were no items in that queue, or some other thread already dequeued all the items that you're trying to enqueue. And it will not return you any book, and it will return false. If it's true, then it will return you a book in this out variable that it successfully dequeued. Queue also has tryPick method to, for example, get this book value if this operation is successful. If not, it will return false, and it will not dequeue it. It will stay in the queue. You will just be able to read its value. There are also other methods on this. I will not show all of them, but the general idea is that you have different methods that can help you to concurrently query or set some information on the data structure. So another example is stack. It's the same as queue, just with another item priority. So you can push items, you can try pop, you can try pop range, you can push range, try pick, absolutely the same idea. You are using these operations without need to log anything. You are able to do it from many threads. There is also concurrent dictionary. It has some more advanced methods like add to update. It accepts a key, an item that you want to add, or a factory that it's running if an item
is already existing and you want to update it. So when you run this method, in case an item doesn't exist, it adds it. In case some other threads already created a book with such a key, then your factory is being run and the item is updated if needed. There is also a method like get or add. When you get an item, if it already exists, or you add a new one. If it doesn't, there is a method try add, which you can call if you do not want to update anything, you just want to add if it doesn't exist, or not do anything if it already exists. And there are methods like try get value that gets a value if it exists or doesn't get anything if it doesn't and returns a boolean. So this kind of methods allow you to write a concurrent code on the collections. There is also concurrent back, which is similar to a regular list from our previous example where we used manual locking. Just it's concurrent, so you can add to this back items from many different threads, and then you can try pick an item without removing it from the list, or you can try taking an item with removing it from the list. Now, one of more interesting collections that you have available in as collections concurrent namespace is a blocking collection. Blocking collection allows you to create some kind of producer-consumer model. So what is blocking collection? Blocking collection is a collection of some items where you specify a capacity, bounded capacity. So for example, 5 will mean that in this collection, there can be at maximum 5 books, not more than 5. And whenever you add an item to this blocking collection, if there are less than 5 items, then this book will be added to the blocking collection. However, if there are already 5 items in the blocking collection, then this call to add will block current thread, and current thread will be blocked until somebody removes a block from this blocking collection. As soon as somebody removes a book from that blocking collection, this method will finally insert that book back into the blocking collection and will continue executing until it will block again because there are again 5 books in the collection. Same happens with taking books. This method take, it will take a book if there is at least 1 book in the blocking collection. However, if there are 0 books in blocking collection, this method will block current thread until there is at least 1 book in the blocking collection, and only then it will take it. So in this example, we are inserting new books every second, but we are taking a book every 10 milliseconds. So we are taking books as fast as we can, but we only insert one in 1 second. And whenever we take a book, we write to console its title. So here you can see title is written only once per second because we are inserting books only once per second. But actually this method is being called every 10 milliseconds. And so 10 milliseconds are passed, then this method is called. It says that there are no books in our collection. And it is being blocked, it is blocking the thread for the next 990 milliseconds until in that 1 second this book is inserted. We can look at that if we pause the application and I mark just my code, we can see that one of our threads is waiting here and another of our threads is waiting here. If I change this to 10 and change this to 1000, then situation changes. Now we will take only once per second and we will produce books as fast as we can every 10 milliseconds. However, as soon as we have 5 books in this collection, we will not add anymore. We will block here the thread until somebody takes it, and only then we will insert it. We can check it. If I pause it and check these books, we'll see that currently there are 5 books here. And if we check our background thread, we see that it is blocked here. It is waiting here on this line until somebody takes it from blocking collection. This is very good opportunity to create a producer-consumer model. However, as you saw, unfortunately, this blocks the thread, and this also blocks the thread. It's even called blocking collection. Can we somehow create a producer-consumer model that will not block any threads, that will be asynchronous? Well, the answer to that is channels. Channels is a new thing that was added to .NET Core for high performant producer-consumer operations. I think it's been used by .NET Core team in different network and TCP sockets related code. And well, this is an example that is similar to a previous one. We create a channel using a method create bounded. It creates a bounded channel with capacity 5, so it can contain only 5 books. We can also create unbounded channel, which will not have capacity. In the blocking collection, we can also create blocking collection without any capacity. Then this method will be able to add as many books as it can. And in our adding method, we are using channel writer write async. And this channel writer write async, it creates a task for us, actually even value task. So it's very optimized. That will add this book to this bounded collection if it didn't have 5 books yet, and if it already has 5 books, this method will non-blockingly just return incomplete task. So this await, it will just it will not use any background thread. It will attach to this task this continuation of the rest of the method, so the next loop iteration. And as soon as somebody takes a book, then this task will insert this book into this collection, will be transferred into complete state, and the continuation will be run. Same thing happens here. Read async, it will read items as long as they are available, and if they are not available, then it will just create a complete task and will wait without using any threads asynchronously until there are books in our blocking in our channel. Channels have different other helper methods like try read, try pick, wait to read async, or completion. Yeah. Also, channels can be configured. So here you have additional configuration for channel, bounded channel options. And you can set a single reader, single writer. This telling that only one writer can write or only one reader can read if you need this. And also you can set a mode. So if you want, for example, for your write operation to actually not wait until there is space available in your channel, but you want to just skip adding new items, you can use drop newest, which will drop new items. No, you can use drop write, which will drop the items that you're trying to write. If you want to still insert that item, but you want to remove the item that is the oldest from the collection, then you can use drop oldest. If you want to still insert the item, but you want to remove the item that is the newest from the collection, then you can, from the channel, I mean, then you can use drop newest. And wait is default strategy, which will make this method to wait non-blockingly again until space is available. Also, one more thing, we didn't discuss yet async enumerable. It's a topic for the Monday, but for whoever knows about async enumerable already, or whoever is interested right now, I'll get back to it on Monday as well, just to recap it. But I will tell about it right now because we are talking about channels. Channel has an interesting method on the reader, read all async, which was added very recently, I think in .NET 8, but I'm not sure. It gets this channel reader as an async enumerable. So you can use await for each on this read all async, because read all async returns async enumerable book. And obviously, on every iteration, if there are no items in that reader, it will just, again, non-blockingly wait until that item is available. So until you close this channel, until you complete it, there is a method on the writer complete that stops it. But until you complete it, this for each loop will execute forever, and you'll just get new values coming in here for you as soon as they are available. Yeah. And I guess it would be the right time to ask if anyone has any questions.
Are there any instructions where is better to use, for example, blocking or non-blocking collection or channel? Because there are different, I would say, instruments, right? But I suppose there are different, I would say, instructions where it's better to use one or another. Do you have something about it?
Yeah, I would say that it is always good to use non-blocking collections everywhere. So you just pick a non-blocking collection that, like for example, channels. If producer-consumer model by on itself, it is very case-specific. So for example, I almost never use producer-consumer model in my code because I almost never need it. So wherever you really need a producer-consumer model, then you can use non-blocking collection or channels. But I would suggest that everyone uses channels because it's a new thing. It works great. It doesn't block threads. Blocking threads is always bad because if you block threads in one of your endpoints on the server and it is being called by 1,000 users at the same time, then you will starve thread pool very fast. All 16 threads, if you have 16 core CPU, will be occupied by 16 first users. And then thread pool will try to create the rest of 900 threads, waiting for half a second before it creates every other thread. So there you have huge delays and issues. So this is why it's always good to never block a thread. I would say a blocking collection deserves to live in the code that is either synchronous and you need to have producer-consumer model there. So you cannot do anything about it. It's already synchronous. You cannot rewrite it to asynchronous, and you need producer-consumer model. Yeah, then this is a necessary evil. Or if you do not care about unblocking threads. For example, if you know for sure that this method is not executed by 1,000 customers, but it's your own, I don't know, console utility or not a web server, or it's a web server, but it's a part of the code that is running on startup or something like that, then of course you can use non-blocking primitives. Yeah, this is answering on the question when to use channels on non-blocking collection. Regarding the rest of synchronization primitives and thread safe collections, well, they all can be used in their own use case. For example, if you need a dictionary and you need it to be thread safe, you can use concurrent dictionary. If you need a QoS stack, you're using QoS stack. So yeah, this is collection related, data structure related, not really thread safety related. The question of when to use which one.
Okay, thank you.
Anyone else? Right, if no other questions, I'll just cover one more topic until we wrap it up. Immutable collections. It's not really a concurrency concern, but I added here in this in these meetups anyway, because they can allow us to write high performant code that is also thread safe. In .NET Core, there were added immutable collections to our language that allow to create collections that are well immutable, so you cannot change them, which means that they can be read by a lot of different threads at the same time without any kind of synchronization, which is very performant, because you do not need to care about somebody adding items to it, because it's impossible. There is immutable array, immutable dictionary, immutable hash set, immutable list, immutable queue. So for example, in case of immutable queue, let's say we create, in case of immutable list, let's say we create a mutable list. And we, since it's immutable, it's almost doesn't make sense to create it without any items. So let's add an item straight away into it. Yeah, I'm already adding items. I guess this is my, well, no, this is not my method. It accepts a book item. Yeah. So we created a new list with just one item, book. Since it's immutable, it means that it cannot be changed. So if we add a new book to it, the instance of this list will still have only one book, this one. In order to get the list that contains both this book and this book, we need to assign it to another variable. So this is the beauty of immutable collections. Adepts of functional programming will totally enjoy this. It might seem that it's very non-performant, right? And non-optimized, because every time we are copying collection. Well, that's the beauty of immutable collections. Immutable collections, they do not copy a collection, because you cannot change it. You cannot change this collection. So there is no reason to copy it to different memory location. Immutable collections reuse the same memory location under the hood. So the separation of adding a book, it creates you a new instance of collections that have these two books. However, the first book in this list will be this book, the book from the first collection. And the first collection will point to this book. So, yeah, how to say it in other words. So imagine a memory, and in a memory we have a list of books. So if we do this, there will be only 5 books in the memory generated. In the memory, there will be only 5 books. Book at location 0, for example, book at location 1, book at location 2, book at location 3, and book at location 4. Imagine that, for example, it's a list of books. It's just that list 5, it will point to book 1, book 2, book 3, book 4, and book 5.
And list 3 will point only to book 0, book 1, and book 2. So under the hood, it's very performant, it's very memory efficient, and these immutable collections allow us to query this data if we pass this list to some concurrent method that runs different tasks, etc. It can query all this data without worrying about this list changing under the hood, because it will never be able to change. Any change will require a new reference variable. So yeah, I guess this is pretty much all I wanted to discuss today. I will just recheck if anyone has any more questions.
Will we cover other topics? I mean, your examples, because we jumped from one to another but missed something. We will cover it later, right?
Yeah, I just reshuffled my program a bit. So next time will be exactly, yeah. First of all, on Wednesday, I didn't manage to cover value task and some of async things, but I decided to move it to the very end because, like, if I would discuss them today, obviously we wouldn't be able to manage to fit all of the thread collections. And also, yeah, on Monday, I am planning to discuss these things that we jumped over, all about parallel in queue, asynchronous streams, so async enumerables, etc.
Okay, thank you.
Anyone else?
Actually, for me, a little bit unclear explanation regarding the memory in immutable collection. Yes, you say that there are some like a reference in memory, and it is it is just a reference, but it is the same like we have for ordinary list. Am I right? Because in ordinary list we have that in case when we have a book, it is just a copy like a reference.
Yeah.
So in case when
see, if we have a list, if we have a list, and for example, I don't know, list, and we have 3 books there. First of all, we can modify that list. That's the main disadvantage of regular collections compared to immutable collections. So we can call add method on it, and it will add force book there. And when we query that list, we'll be able to get all 4 books.
Yes, it's clear. But what about memory? Your explanation about memory, that's it's related. That's another copy.
So this is a memory. Let's imagine this is a memory. So in memory we have 4 books right now. And if we want to create another list from this list, for example, we use list copy method. It will copy completely all 4 items, right, into a different memory location. So we have list 2.
Yes.
Okay. And now if we use a method list to add, it will add a 5th book here, and now we have 5 books in list 2 and only 4 books in list 1, right? However, in immutable collections, for example, we have a list with 3 books. We cannot add item to we cannot add item to this list. This list will always have only 3 items. We can only call a method add on it, which will return us another list. And it will add that forest book here. Yeah, right, like in regular list. In memory, it will look like a regular list. And in this list too, we'll have 4 books. However, this list, it still has only 3 books. It will only take 3 of them.
Basically, immutable collections, they store the handle to the start of the collection and the count of items that it needs to take. We can think about it like this. So if you add another item here, it will add fifth item, but this list will still have 3 items, this list will still have 4 items, and a new list that you assign to a variable calling method add, it will have 5 items.
Okay, thank you.
So based on this explanation, that if we go to our code, list 3 will have 5 items if we have 3 items initially. No?
Well, list 1 will have only 1 item, list 2 will have 2 items, list 3 will have 3 items, list 4
3. Okay.
It's because we are adding these lists in memory very efficiently. We do not copy them, but the list itself, it has a count and a reference, so it knows which element is the first one, and it knows how many it should take. It's similar to slice operation, I guess, in JavaScript.
Okay, thank you.
Anyone else? All right, if no more questions, then have a good weekend, guys, and see you on Monday regarding all the parallel linking and other async stuff. Thank you for joining.